Yeah.
This meeting is being recorded.
Respected senior members of INS and friends, it is my great privilege to welcome you all once again to this INS webinar. And we, as you know, we call eminent speakers and unit heads from BAE and other industries, academia for this webinar. And it is indeed important to know and update ourselves about the recent developments in the field of science and technology in general, and nuclear engineering and other societal benefits from nuclear science in particular. The present INS committee is committed to organize scientific programs, of which webinar is one of the important activity. Today we have with us Shri K. Ravishankar, General Manager in charge and Corporate Head R&D, BHEL Hyderabad, who has kindly agreed to give a talk on an introduction of advanced ultra supercritical technology as a consortium member of this important project of the country. This AUSC is also called 700 degrees technology because of the uniqueness of this project. So on behalf of INS and on behalf of the INS webinar committee, I welcome you, sir, to this INS webinar, which is 30th in the series. So, and I think members may remember that our 21st webinar was given by one Shri Neeraj Sinha of Niti Aayog on the indigenous development of advanced supercritical technology from the government point of view. Today we will hear Ravishankar, who will be talking about the R&D activity that is carried out in BHEL. The advanced ultra supercritical project is being developed under the consortium of BHEL, IGCAR and NTPC. The technology under development is the most efficient power plant in the world. It's going to be the most efficient power plant in the world when it is deployed. So the supercritical here means the process operating is above the critical point of the water, where the liquid and the gas phases of water coexist in equilibrium. There is no difference. Actually, there is no difference between the two phases of the water. So the AUSC will also have participation from leading national academic institutions, industry partners, and material development companies. IGCAR has also played an important role in development of superalloys such as 617M and 304MCU for the boiler tubes, 617 for the turbine rotors, and 625 for the casing of the turbine casing. For achieving the net efficiency of the plant to be more than 35%, CCS, that is carbon capture and storage technology, is the most important, and a lot of R&D activities have happened. Such an industry is also called a HELE industry, essentially meaning high efficiency and low emission industry. Shri Ravishankar is going to speak more on all this. I once again welcome you, sir, to this webinar, and I thank you for agreeing to give a talk to us. So to briefly introduce our speaker today to the audience, it is my great privilege to read his brief biodata. Shri Ravishankar did his schoolings and in UP, and B from Motilal Nehru Engineering Colleges, Prayag, in 1985. Further, he did his MTech in Manufacturing Technology from REC Trichy in 1989. He did his MBA from Indira Gandhi National Open University in 1995. And MA in English from Annamala University 2016. A wonderful combination indeed. He joined BHEL Trichinapalli unit in October 1985 as an engineer trainee and worked in product engineering department for 25 years in functions of boiler pressure parts and boiler layouts. He also worked in the material management functions between September 2013 to May 2015. From May 2015 to May 2018, he was heading the engineering function of fossil fuel boiler group at Trichy unit. From 2018 to 2021, he worked in the mission directorate of Advanced Ultra Supercritical Power Plant Technology Development at BHEL Corporate Office, New Delhi. Members may remember that our Shri was the mission director of this project. So perhaps he was also in the directorate. So wherein he was responsible for successful completion of R&D phase of development of various technologies for this power plant in the area of boiler, which were indigenous development. Subsequently, he worked in the area of hydrogen business, wherein he worked for the green hydrogen-based pilot projects, technology collaboration, and in-house technology development of fuel cell and allied products and systems. From March 2022, he has been given the responsibility of leading the corporate R&D functions of BHEL. Presently, he is working as general manager in charge of BHEL corporate R&D based at Hyderabad. So this is his a very brief introduction. There are many more things to say about him. So on behalf of INS, I welcome you, sir, again, and I request you to begin your presentation to our members. Thank you. Thank you very much.
Sir, thank you so much for giving this wonderful introduction from me. And I'm extremely grateful for the INS to give this opportunity to me to tell about the development work, unique development work, which was jointly done by the three well-known organizations of diverse functionalities coming in unison and giving the country the indigenous technology development. In my presentation, I would like to showcase the genesis of the AUSC, the background, the whatever groundwork were done by the governmental agencies, and then the technology development, what was done by the consortium, what are the end results, and finally, what are the takeaways and the lessons learned. So with the kind permission of the chair and the august members of the team, I would like to start the presentation, sir.
Please, please.
So this is the title as title read, sir. Overview of the Indian AUSC Advanced Ultra Supercritical Program. So the genesis actually of the Advanced Ultra Supercritical Boiler Program goes back as October 2009, when the Principal Scientific Advisor of the Government of India, they had organized a series of meetings, as it read, to have the mission document for the national mission for clean coal carbon technologies. So under the this National Action Plan on Climate Change. So this project found a very important place with its enhanced efficiency among the thermal plants and the whatever the emission reduction what was achieved by using this technology, sir. So as it goes, sir, the project on the development of AUSC technology for power plant was considered the most important at that time, and accordingly, none other than the presentation was made to Honorable Prime Minister in the November 2010 by Dr. Baldev Rao, then Director, Indira Gandhi Center for Atomic Research. IGCAR, as needless to say, they have been right from the earliest time they have been involved in the project, sir. And the presentation was attended by all the senior administrative members of the Indian administration, sir. PSA, namely the PSA, of course, Secretary Department of DAE, Ministry of Power, of course, Dr. Baldev Raj, and CMDs of both NTPC and BHEL, sir. So in that particular meeting, way back in 12 years back, sir, this Honorable Prime Minister had given the consent for the implementation of the proposed submission on the development of AUSC technology. So genesis of the AUSC technology goes back as 2010, sir. And at that time, on the administrative side, it was decided that, sir, advanced ultra supercritical boiler technology R&D phase will be taken forward by the Department of Heavy Industry, preparing a cabinet note for the approval of the grant for the particular project, sir. And the Ministry of Power was given the mandate of prepare the cabinet note for setting up the proposed 800 megawatt advanced ultra supercritical. They call it a technology demonstration plant, TDP. It was termed, sir. So these both the things were decided at that time. Accordingly, activity got commenced, sir. So the AUSC initiatives, based on this discussion at the highest level of equivalence of power, sir, the consortium of IGCAR, the BHEL, and the NTPC was then formed by the PSA's office in August 2010 for the development of advanced ultra supercritical boiler technology for power generation through indigenous effort. The underline of this thing, whatever we'll see in the subsequent slides, sir and madam, this the total effort was indigenously done. Although materials were not available, but the total technology development, every efforts were taken indigenously by these three group to have the Make in India concept way back in 2010 itself, sir. So accordingly, a MOU was signed on 26th August 2010 for the successful and joint implementation of the submission, sir. And of course, it was very clear at that time, sir, the consortium will draw the strength and technology availability with academia and research institution available in India for the in the due course of implementation of the R&D activities. And it was done, sir. It was done. Subsequently, we will see how it was done, sir. Actually, sir, to give a fill up, although the project approval on the DHI funded project for AUSC phase 1, it came maybe much later. Under the PSA's office direction and guidance, 10 projects were taken to continue on to initiate the work on the R&D work, sir. So pending, that's what it says, that pending the approval of the cabinet committee, the R&D work was started by granting of 10 projects by PSA's office, sir. The projects were mainly taken by Bharat Electricals Corporate R&D, WRI Welding Research Unit Tiruchirappalli, and IGCAR, sir. Those 10 projects laid the backbone of the first foundation stone for the technology development for the advanced, namely advanced ultra supercritical technology, sir. Namely, to say a very important project, the fabrication project of high pressure bypass valve for the mainstream application was taken by Trichy Valves Group. Similarly, in the fabrication of 9 chromium 1 moly quarter vanadium steel SA213 T91 for the enclosure application was taken by WRI. These were the very major project which is to make the manufacturing and design requirement for the AUSC technology, sir. Subsequently, on 10th August 2016, finally CCA had approved the phase 1 project, sir, the main R&D phase of the proposed project. The duration was stipulated as 2.5 years, sir, 30 months, and costing around 1554 crores, sir. 900 crores was granted by DHI, sir, Department of Heavy Industry, Ministry of Government of India, and 550 crores were contributed by the 3 consortium partners, sir. IGCAR's contribution was to be 234 crores, NTPC's contribution was 50 crores, and BHEL's contribution was 270 crores, sir. As you could see, as mentioned by our honorable senior members of the INS team also, there's no plant as of today, even today, there's no plant exists based on the AUSC technology. The steam parameters of 710 degrees centigrade and 310 bar pressure. So the technology, the boiler design stipulated that it will have overall efficiency of 46%, which is more than by around 4 to 5% of the so-called ultra supercritical boiler technology based plants which is coming up in India, which has come up in India with a at design parameters of 590 degrees centigrade of steam temperature, sir. Now, so that actually this, as we had talked about the phase 2 of the technology development demonstration plant per se of 800 megawatt, it was stipulated that at that time, based on the information available, it will take around 4.5 years to complete the phase 2. So total time duration stipulated in the note was around 7 years, sir. 2.5 years for the R&D. Very, very challenging timelines for given the fact that so much of development has taken place, and 4.5 years subsequently for the phase 2, sir. Now we come to the roadmap what was put for the consortium partners. If you take IGCAR, it was for the advanced design analysis, material development, manufacturing technology, testing and evaluation. BHEL was given the responsibility of development, design and manufacture of power cycle equipment, system engineering, test loops and evaluation. As far as NTPC was concerned, there were detailed project report, project management and operation and maintenance based on their nature of it was decided based on the capabilities and capacities available of the consortium partners. So, as I had mentioned, sir, the 10 number of pre-project, actually the project which were sanctioned by the PSA's office, they were termed as pre-project activities because they were taken up before the sanction of the DHI sponsored phase 1 R&D phase. So some seed money was put by PSA. It was to the tune of around 60 crores for taking up those projects, sir. And the most important thing is utilize gainfully the lead time from the date of the signing of the MOU by 3 consortium partners and to the actual sanction. Actually, it amounted to be almost 6 years, sir. 2010, the MOU was signed, and August 2016 was the government note on the proposal of R&D phase was done. 6 years were there in between. So these projects made a very good fill-up. And the very important point was the consortium is held together and works together. These projects led to the fact that regular reviews took place with the formation of many committees, which I will talk later. And these projects held together a consortium because they were deeply involved together for the formulation of technical documentation, procurement, and the project per se to be done for the AUSC technology developments. So this is the facts that a project review and monitoring committee was constituted to oversee the project monitoring and guide the scientific technical work, sir. Why I stress on the guide is these forums, they were the most instrumental one in guiding, course correcting and advising the technical teams of all the 3 consortium partners through their very detailed technical reviews and advices and suggestion to the technical fraternity of the 3 groups, sir. So as mentioned, sir, C. Subhash and Chetal, former director in IGCAR and honorary scientific consultant, ultra supercritical boiler plant, and he was the guiding force behind the AUSC program, sir. It was his effort which led to the successful technical closure of the project within a very tight schedule, sir. Although there was some extension, but they were to the minimum, and most of the project we could complete within the stipulated cycle time. Very, very challenging time of 2.5 years, such a project where procurement of equipment, exotic equipment, niche equipment, nickel-based alloy materials, and further formulation of manufacturing plans and testing plans, they were envisaged, and including the establishment of 2 testing facilities, one in a boiler, one at R&D. So these all were involved, and a very challenging task was completed. So the consortium also prepared very important things, sir. A comprehensive report for material selected for the prototype, and a very important document, 200-page document was prepared, sir. Project design memorandum for the paper, which in detail outlined the design philosophy, materials to be used, and the total concept behind the power plant design that included the boiler per se, critical piping, and the turbine also, sir. Because these are 3 areas where the high temperature will call for major design changes from the conventional supercritical boilers, and a very deep rooted approach to the material selection, sir. So this was a very important document which was comprehensively made by the consortium partners, sir. And that became the guiding force for the project to be driven. Another very important document which became the, I can say, Guru Mantra, or the base document for identifying 136 and odd project for the AUSC was a gap area document, sir. It's a, as we can understand, for any establishment of new technology, all the products were reviewed based on the available technology, available material information, and available expertise vis-a-vis what is required. Based on that, gap areas were identified, and they led to the formulation of technical projects to be taken up by the consortium members. I would like to submit to this August forum is the total number of projects what were taken under the excuse me, under the R&D phase 1 was 136 numbers, sir. 34 projects were taken up by IGCAR. NTPC had taken 16 projects and remaining around 87 projects were taken by BHEL. And BHEL basically corporate R&D, our heavy equipment plant, turbine plant in Haridwar, and high pressure boiler plant at WRI. 3 entities were mainly involved for projects on the turbine and material testing as well as the boiler components. So this was the, just to give an idea that these many number of projects were taken up and successfully completed within the time frame with some extension of the some projects that I will outline when we go through the presentation. So how the project was guided, the success behind the successful completion of the project meeting the technical requirement was an administrative structure, sir. We had an overarching committee and we had a project review monitoring committee. So the project review monitoring committee, as I has told, it was a base for the technical reviews, very critical technical reviews with timelines, bottlenecks, how to debottle them, and planning for the further course of action for the successful completion of milestones. And as I had mentioned, sir, Mission Directorate, a full-time Mission Directorate was constituted in May 2017 as Shri Subhash and Chetan Sahab as a Mission Directorate. As it was mentioned in my brief mention, I worked with the Mission Directorate for 3 years. I was working under Chetan Sahab along with some of my colleagues, and I was given the responsibility of completion of the project related to the boiler and critical piping. They amounted to around 18 numbers. So other than the Mission Directorate, we had a unit level project execution committee. Unit head was responsible for ensuring the milestone completions and the project deliveries of each project. We come to the broad activities of the project, what was stipulated in the program, sir. Design of the components impacted by AUSC stream parameters and design review of the key components by foreign experts. Sir, I would like to submit here is the total pressure part and turbine construction was impacted by the AUSC stream parameter because the total, there was a paradigm shift of material of construction from the so-called supercritical or ultra supercritical boiler compared to AUSC, sir. There will be a small one slide in which I would like to explain the material shifting, sir. So that becomes, so it happens. So the total boiler design, turbine design, the critical valves of main steam stop valve and high pressure bypass valve, they become the necessary component of the review by the third party, sir. And design of steam turbine with the exotic material was undertaken. The most critical and most important and most challenging task among the AUSC R&D project was design of steam turbines, sir. So that took the, in the our total time schedule, that took the maximum time, rightly so, because such a design is it's not available anywhere, and it took a lot of time for doing a very deep design of turbine components and getting it reviewed by the competent parties. And coming again, as it was discussed, a very good discussion happened. The supply of the material indigenously. I am very proud to tell here that indigenous production of material for the boiler tubes, valve forgings and turbine castings were happened. The turbine casting, intermediate pressure turbine casting was successfully manufactured in BHEL Central Forge plant, sir. The biggest casting of its kind in the world, weighing around 21 tons as a finished weight. Subsequent slides, you can see the photograph of that, and those, that's a very proud moment for country as such, more so for BHEL, to be able to successfully develop that. And Midani supplied many of the valve forgings. We got products from Midani, and and the forging for the mnemonic 105 blades also were successfully manufactured at Midani plant and supplied to Haridwar plant for the machining, sir. Very proud moment for Indian industry indeed, sir. Again, continue with the broad update of activities, sir. Establishing the manufacturing technology for the boiler and turbine component. Here, as I had mentioned in the initial discussion, sir, the entire manufacturing technology for the critical components for the boiler and turbine, they were established. Manufacturing process was written. Technical delivery condition or engineering specification for all the materials to be procured. New materials of nickel-based alloys and other stainless steel higher-end alloys were made in consultation with the material suppliers. Some cases there were multiple, like 617. We have many suppliers. In case of some material, they were like Sanicro 25, which is a austenitic stainless steel. We had it was proprietary at that time. And of course, the 740 grade still is a proprietary. So technical specifications were prepared by the units under the able guidance of mission director. And they were taking in consultation from the material producer, so that we had a perfect quality material meeting the requirement of the chemistry, metallurgy, and the other requirement of boiler and turbine application. And second one was engineering facility for corrosion evaluation of boiler tubes and design of the steam turbine rotor. At this point, I would like to mention this facility was established in third unit of the 4 number of 210 megawatt unit of fossil-fired unit situated in Dadri of the NTPC plant, sir. Further details will be there. Technical details are coming up in the presentation. And turbine rotor testing, as I was mentioning, it was established in the corporate R&D premises, sir. And a national research for material evaluation testing. I'm very proud to today announce to this very August forum that very high-end inspection and testing equipments were procured under the AUSC banner by BHEL, IGCAR, and NTPC. They are available in their respective IGCAR and R&D center of Netra of NTPC, and in BHEL. Manufacturing equipments and testing equipments are available in Welding Research Institute and Trichy plant of Thurmayam, and boiler plant in tubular products in Trichy, and corporate R&D. So they were created for the establishment of manufacturing capability in the units, and testing equipment for testing the various material of construction, which will be used in the AUSC power plants. So maybe AUSC technology at that time, it was significant from the point of view of reducing emission and increasing the efficiency of the power plant. Ultimately, it resulted in lesser CO2 emission. So that was a main clean coal technology to address at that time, sir. And at that time, just to update the August forum, certainly you'll be also knowing that many old subcritical plants of the smaller capacity, they are now superannuating. They are 35, 40, 45 years old. So thinking in the minds of the planners was that those plants can be replaced with the AUSC technology too, given the time frame and the investment granted. So we come to that advanced ultra supercritical boiler technology. Why? We know that for that, whatever it may be, coal will be the integral to India's energy security, sir. And whatever renewable energy may so, at least 40% of the power may have to come from coal-based plants. So AUSC will serve as a very ideal tool for addressing this coal-based plants. That is the thinking based on which was one of the vital point for driving the AUSC technology R&D, sir. Now, sir, we come to the steam turbine path. You can say supercritical, we had 565 degrees centigrade. The term ultra supercritical is only these three terms that I would like to just elaborate here. This are with respect to only the temperature, sir, and the definition given by various manufacturers. So we had supercritical design where we had a 568 degrees centigrade. Ultra supercritical design when the steam temperatures touch 600 to 610 degrees. When the advanced ultra supercritical technology, when the steam temperatures are 700 degree and above, sir. So that is the classification which is in our steam power plant. That definition is given as such, sir. So this is the thing. Already I have explained about this thing, sir. I will just go ahead. Now, so this particular mission directorate, as I was said, 2017 was established, and mission directorate was fully empowered for the selection of manpower and financial structure. I would like to submit, because these are very important because the total DHI funding came to mission directorate. It was a third entity. It was constituted by DHI, and we had the total finances were distributed by mission directorate to the consortium partners, and mission directorate was responsible for the accounting of the funding given by DHI, sir. And of course, senior level nominees were deputed to this mission directorate from all the three consortium partners. They worked for the successful completion of the project in their own respective areas. Now, sir, we'll come to the technology part. What are the major areas of work identified, sir? Design and design review of boilers, of course, by experts. What we have done, sir, the design during that consortium meeting, it was felt that we are designing the components with new materials of construction, which is totally different from the earlier existing one. Even in the total component, there is a parting and shift of material to the higher side. Products are having different kind of material. So it was decided it's prudent to have the design reviewed and vetted by competent parties. So that was taken up. Both boiler and turbine designs were made and reviewed by competent parties. Their comments were taken. They were reviewed and the designs were modified with the comments given, and it was finalized and it was accepted by the consortium partners. Come to the manufacturing. Manufacturing technology, basically it was welding and machining. Mostly in boiler components, it was welding of, I can say, the bending of tubes and pipes, and machining mainly for the turbine component, rotor and blades, rotor and casing, sir. So the turbine rotor, as I said, rotor and casing, the rotor was made of alloy 617 forging, sir, and casing was made of alloy 625, sir. And I would like to give a feedback to the August forging, sir. 617 was taken as the material of construction, material of use and design in the boiler, sir. 617 got both tubes and pipe specification. And when the designs were completed with that, when the bill of material was prepared, so it was found and the casting was done for the technology demonstration plant, it was found to be quite on the higher side. So immediately the consortium partners, along with the mission directorate and other allied groups, they had started having a rethinking on the material usage in the pressure part components, including critical piping, and many options were studied. And the consortium came up with the final suggestion of using this Inconel 740 and Sanicro 25, sir. Actually, Inconel 7, it should read as Inconel 740H. Actually, I'm sorry. Inconel 740 was developed by PCC, and that material was not found proper for the pressure part application. Subsequently, and it was discarded at earlier stages of discussion. Subsequently, PCC developed a modified version controlling the finer elements of material metallurgically, and they made a new material in Inconel 740H, which was taken up as a alternate better material of construction. And it was found that the mechanical properties of the 740 is much better than alloy 617. So again, we bought the tubes and pipes of the 740H specification, and we did the establishment of manufacturing technology for the material of construction of pressure part, which led to the optimization of the overall boiler weight and cost, namely most costs. Sanicro 25 is a austenitic stainless steel, sir, and it was a proprietary steel that was used in place of Super 304H, sir. So both the materials were, again, they were procured and the testing was done to establish the manufacturing process for the various components. Now, sir, we come to the material data adequacy was checked, sir. So material data basically for the turbine components were extensively generated in the lab testing in BHEL, IGCAR and NTPC, sir. And parallelly, national institutes are also were given the samples, and mission director along with the help of IGCAR, the material data for the usage in the design of turbine rotor and casing components were developed, sir. Second point, that as I said, corrosion test facility was established for the material to be used in the AUSC, and turbine rotor test facility for the, sir, actually this, in this case, I would like to submit to this August forum that the turbine rotor test facility we have planned for a monometallic and bimetallic both rotor. Monometallic in the case of HP turbine is going to be only a single construction. In intermediate pressure turbine, the rotor was optimized by using the high temperature zone, the nickel based alloy, and the low temperature zone, the conventional material. The subsequent slides, there will be a sketch to explain that, sir. And of course, system engineering was done. Total power plant system engineering was done as it is done in the case of a regular project, sir. So these were the basic tenets of the material selection, which were on based on which material selected were evaluated, sir. Adequate mechanical strength at such a high temperature was critical, and corrosion resistance, of course, weldability and manufacturability were the key issue, sir, because in boiler components, welding is the only thing, and manufacturability in the point of successful bending for various radius of bend, which one will encounter in the boiler pressure parts. This was the critical criteria, sir. And I would like to submit that earlier discussion, what happened, availability of material, although it may not sound too technical, but that was one of the very critical point when you are going to execute a project, sir. Even during our R&D phase, when we are sourcing for the materials, suppliers, we had great difficulty in identifying the suitable supplier, supplying the material of those grade, meeting the technical requirement, what we have stipulated for this plant, sir. And ultimately, sir, when success of any project to be pushed forward, to be presented in overall economics, whatever material changes and design changes we mooted, that was to address the final point, overall economics. Now, sir, I will come to the chemical. Okay, basically, this slide is to highlight how the paradigm shift has happened compared to the supercritical boilers, ultra supercritical boilers versus AUSC. In, sir, our supercritical and ultra supercritical boilers, basically ferritic steel of that 2 and quarter chromium 1 moly T22, 2 and quarter chromium 1 moly with tungsten T23, of course 9 chrome 1 moly steel with 1 quarter moly T91, and T91 with addition of tungsten T92. They are extensively used, sir. Added to that, in high temperature zone of our superheater reheater, where the medium temperature touches 590 or 600 as case in the case of ultra supercritical, we go with the super 304H, sir. When it came to AUSC technology, sir, our total, the T22, T23 were totally eliminated, sir, and they were replaced by T91, basically more of T91. And in case of stainless steel, we replaced super 305 by Sanicro, and extensively in all the high temperature pressure parts, pipe, tube, or interconnecting pipes and all the components, we went for 617 and 740, sir. And of course, in the turbine, we have gone with 625 casting, sir. So this is the paradigm shift what we had experienced. And of course, this has led to the high overall cost of the projects, sir, because of the maximum use of nickel-based alloys, which are very expensive in nature compared to the ferritic or regular austenitic steel alloys. So, because when the average test to rupture was taken as 100 MPa at design temperature, so thickness, to maintain the same thickness for the better flow and performance requirements, nickel-based alloys become unavoidable, sir. And for 740H was found more suitable compared to 611 because of the excellent enhanced mechanical properties, which resulted in a lower thicknesses, and in some cases even the diameter change also, sir. And corrosion resistance, major shift what we can say, sir, in our enclosures, all the gas tight enclosure, what is called as a furnace, or what you call as fin welded panels, which encompasses the total pressure part. Our USC boilers or supercritical boilers are 2 1/4 chromium. That was totally replaced by 9 chromium steel. This one single change, one can imagine who have worked with this 9 chromium steel, how much of manufacturing cost and time and carefulness has to be increased. So that was a major shift with respect to the cost in the procurement, cost of manufacturing mainly, sir. So that was the reason. And of course, Super 304, as I said, Sanicro was replacing Super 304S, sir. Arsenic stainless steel, we could not use it. Even in conventional barrier, we use it because of the poor physical properties, sir. Now we come to the economics of this plant, sir. Nickel-based alloys are certainly more expensive, sir. And actually, sir, when we checked the cost of the material, we took budgetary offer when we were preparing the pillar material, and costing was done for the technology demonstration plant. The nickel-based alloy cost is around 25 to 30 times more than the cost of this 9 chromium 1 moly steel T91, T92. So to give an idea, sir, the range of nickel-based, that 9 chromium 1 moly steel hovers around 2 lakhs per ton, whereas the nickel-based alloy at that time, it hovered around 77 lakhs to 1 crore per ton, sir, depending on the product form. And of course, sometime quantity. But basically, what we have found that this cost is 25 to 30 times more. So economics became an important parameter, and that led to the change of the material of constructions. In Coral, as you can see, sir, boiler tubes we replaced by 740, and the mainstream piping we replaced by 740. The 740 could not be used for hot reheat applications, sir, because the pipe size manufacturing was not possible for the requirements, sir. So that's why we had to be content with 617. That we have retained 617 only, sir. Of course, this chart technically depicts the ASME allowable stress value, sir. So it shows the comparative figure of where we stand vis-a-vis the material of construction, starting from 2 1/4 chromium 1 moly steel up to alloys 740, sir. Based on the economy, based on the temperature requirement, design requirements, the materials were suitably selected, sir. So quantum of 740 is maximum, sir, followed by Sanicro. Super 304H finally is eliminated. So as the alloy 617 tubing, except the tubing which is not coming inside the hot heat transfer area, sir. And T91, T92, especially T91 is major portion is, total portion is used in enclosure. T23, T22 are eliminated in this design, sir. So now in my this presentation, sir, these following slides will show the actual development of the building and the various manufacturing process, sir. These were done, the photograph what I'm going to show, these are done in our building research institute, sir. You can see the different bending and welding process are depicted pictorially here, sir. These are the tube which were supposed to be used for our pressure part fabrication. In the bottom one, you can see that the squeeze, what is called a squeeze bend, when the radius of bend is equal to diameter or less, that is the innermost bends of our heat transfer areas. Most critical because you have to maintain the radius without any ovality and thinning going beyond the requirement stipulated by the boiler code, sir. Similarly, the diameter, you can say the size of the tube 52 by 11.9, which is the stipulated size of the tube in the high temperature pressure part application, sir. You can see the bottom one, the swaging we do, because swaging is required when the diameter changes in the boiler pressure part heat transfer area, sir. Swaging is alternate method of welding a reducing insert, sir. So reducing insert may cost more because manufacturing cost as well as the welding cost. But herein, this swaging is accomplished in a single stage. So this was also based on the requirement of the boiler design. These are also established in our shop, sir. Now this same thing, whatever we did with 617 tubes, you can see the same were done with the 740S tubes also. RBD ratios of 2:3:4. You can see pictorially they were established successfully in our shops. These are the configuration I would like to narrate, which are taken really the one-to-one from the boiler design, which was made for the AUSC TDP, sir. Here you can see that with Sanicro, similar weld and dissimilar welds are also done. Building process are developed pictorially. We are depicting that in this photo, sir. Now we come to the very critical point of this. We call as a header, sir, or a manifold, where one system tubing gets connected before going to the other system, sir. So this is a header which was taken. You can see the size of the header, 457 by 120 mm thick, 6-on pipe, which is the selected size for the mainstream outlet header in a AUSC power plant, in boiler. And this was procured. The typical tube to pipe welding process were established. They were welded. They were tested for all the IBR related requirement, ASME related requirements, and they were also tested hydraulically for the weld integrity, sir. So the prototype of product, albeit in a shorter length, the header length was around 2 meters, sir. It was manufactured in our WR Welding Research Institutes. These are the actual bending of the pipe, sir. In boiler, like in other nuclear power plant or other plants, we'll have the interconnecting piping. Piping is always of higher size. You can see that this in our Tirmayam plant, we have got a pipe bending machine where they were successfully induction bended. The pipe size were, in case of mainstream line, it was ID 315 by 95 mm thick, sir, for inconal 6-on material. And same thing when we substituted it with 740H material, the size became ID 315, inside diameter 315 by 47 mm thick. Almost thickness was reduced by 60%, 70 to 80% in that case, sir. So this is the pictorial, just a picture taken during the bending, sir. Now just the same what I said, sir, that just a text is just depict what I said. Now this is, sir, in case of the mainstream line, the high pressure bypass valve was designed indigenously with the help from mission director mainly, sir, and the designs were vetted through the third party. So this was successfully manufactured, and I would like to submit to this August forum is this valve has been accepted by NTPC to be put in as a test example in their North Kanapura 660 megawatt plant for a testing purpose, sir. This valve is going to be really on live for the real-time testing and examination of the valve design and the material integrity, sir. Similarly, superator safety valve also was manufactured, sir, in-house in our boiler valve shop for the parameter of 355, design parameter 355. And in this case, sir, as I mentioned, indigenous supply of alloy 617 forgings were there from Midani, which were used for the construction of the safety valve, sir. So now we'll come to the turbine rotor, sir. So the intermediate pressure basic construction for a supercritical is we have got that X12 CRMO material and the X19 material, that's the blades. In first of all, what we did was, sir, actually the total rotor was conceived with alloy 617 forgings, sir. It proved to be a very costly affair. Then rethinking was done, and what was done was we went to a very novel concept of welded or bimetallic rotor, wherein the high temperature zone alone, when the temperature was beyond the limit of X12 material, the alloy 617 was used, and at the both ends we had gone with the regular material of construction. So that was termed as a welded rotor, which is a very, so far in none of the supercritical boiler till our time, it has not been used. So ultra supercritical boiler will be a first time in the project come, we'll have a welded rotor in place, sir. The rotor, as I was mentioning earlier, sir, 900 millimeter average diameter, that total rotor 1-to-1 around 12 meter length, it was, the material was procured, the rotor was machined, the blades were inserted, and the total rotor was constructed in our Haridwar shop, sir. You can see the welding of the rotor. The machine came from Shasmide, and these rotors were from Shasmide, and welding machine equipment was also it was from France. So the rotor was 1:1 size rotor was welded in our Haridwar shops. Similarly with casing, sir, you can see that based on the temperature profile, the intermediate pressure inner casing were constructing of the regular material, and the brown material says it was the inconal part. The lower, it was constructed in two parts, are upper and lower. I'm very proud to say, you can see that the lower part, alloy 625 casting being taken out. Just it was a photograph was taken when one of the project review committee meeting was happening, and all the dignitaries were present. In front of them, the casing was taken from the furnace and it was water quenched. This casing weighs around 21 tons. It is the highest weighing casting of its kind in the world, sir. 21 tons. It was made successfully by our BHEL Haridwar plant, central forging plant, sir. Coming to the blades, sir, as I was telling, the alloy 6001 blades are successfully machined in the state-of-the-art manufacturing facility available blade shop in our Haridwar plant, sir. And subsequently, when there was a design change given by based on the comments of the reviewer, the blades were changed to mnemonic 105. I'm very proud to announce to this August forum that mnemonic 105 forgings were made in Midani, supplied to BHEL Haridwar plant, and the machining of that blades were successfully done, sir. So that's a very classic example of, albeit Midani was not able to give very big size rotors, but I'm sure that many of the components of the AUSC, they were developed indigenously by Midani with the great efforts, and that made in India Atmanirbhar concept seed was sown at that time. Now I am going to talk a few details about our corrosion test rig. Excuse me. Sir, it is put in the Dadri 210 megawatt fossil fired plant of NTPC situated in Dadri, Ghaziabad. In the schematic of this, as I was explaining earlier, so this is, we are tapping the steam at 540 degrees centigrade and 136 kg pressure from the main steam line. A loop, 4 number of loops connected to one number of inlet and outlet header. The circles what you see in the pictorial representation are the headers, sir. There are 4 number of coils hanging in the furnace. There are flow measurement, temperature measurement equipments are 4, and control valves are installed. The outlet steam temperature is 720 degrees centigrade, sir. The 720 degrees centigrade is there the pressure reducing valve is there. The pressure is reduced to 45 kg, and we have got a mixing piece in which the hot steam of 740 degree is cooled to 550 degrees centigrade by taking the tapping from the low temperature superator outlet steam, which is at 390 degrees centigrade, sir. So that lower temperature steam of 545 degree, 540 degree plus or minus 15 degree, pressure 45, it is joined to the hot reheat pipe and is recirculated in the boiler. The flow taken was around 20 tons, sir. And you can see that there are 4 number of assemblies, and each assembly has got 2 elements. And the flue gas temperature at this zone is around 1200 degrees centigrade, sir. Now we'll come to this is the construction, sir. You can see the physical arrangement. The total overall length of the so-called heat transfer element is 13 meter inside the flue gas path. The horizontal line shows the furnace top. The coil is hanging inside the furnace hot temperature zone. The inlet and outlet manifolds are outside the flue gas path. You can see above the center line of furnace. And the material you can see, sir, we have put all the material what was to be used in the AUSC boiler construction, namely 617, Super 304H and T91. Number of assemblies 4 and number of elements 2. And I would like to update, sir, when the 740 tube was to replace the material of construction for the tubes and pipes, in this test loop also we supplied a new coil which had the 740 material and Sanicro material as included. one number of coil we had manufactured and is erected at Dadri site, so that we will get an experience on the latest material also with respect to the hot temperature, corrosion, and other material properties when it's exposed to the hot flue gas. This you can see, sir. This is inside the photograph taken. You can see the enclosures and the 4 number of coils after erection inside the furnace. Sir. It is hanging from the top. This is the control room dashboard, sir. Because this test loop is a standalone total equipment, which is all control mechanism and a feedback control system like any equipment will have in any plant. You can see the total control dashboard, various parameters are monitored, and there is a provision to capture data online and provide it to the consortium partners for their review. So that also provision was made. The test loop actually, because of the COVID and other low power requirement, it has not been operated earlier, but now it is operating based on the demand requirements. To submit to this August forum, this test loop was successfully commissioned on February 2nd, 2019, and it was sort of dedicated by respected chairman, BHEL chairman, and of course our directors and NTPC directors on the 9th of February 2019. So now we will, these are the development what I have shown in this time period, sir. To give a final update, that projects were taken on the boiler components, turbine components. Design were made for the total boiler components, total turbine design, rotor and casing design was made. It was reviewed twice by the competent authority. First time taking the corrective action, and the second was for the final review. It was excuse me, validated by the competent person. The total manufacturing technology was, documents were prepared, and it was successfully manufactured. And I would like to submit to this August forum that lower casing, for which we didn't have a facility in the in-house BHEL premises, Shri was contacted, and they kindly accepted to do the NDT of the such a big casing. The casing was moved to Shri. It was done and it was brought back, sir. So that type of cooperation did exist when the AUSC R&D project was going on, sir. And all the I'm very proud to submit to the August gathering. The project completion was one mandate. A very elaborate, detailed documentation of each activity of the project was another mandate. All the project detailed technical documents were prepared. They were reviewed by the mission directorate personnel, finally reviewed, commented upon, advised by mission director. And after doing the final correction, they were submitted, and they are with the consortium partners. Very detailed documentation were made for all the projects, sir. And now we'll come to the implementation, the lessons learned, sir. So very proudly I can declare, sir, the AUSC R&D project is a demonstration of successful implementation of a challenging R&D mission with number of first, like superheater header and alloy 6 and so on, turbine rotor test rig, dissimilar metal weld joints, executed by 3 consortium partners, having diversified expertise. And this can become, already is becoming in BHEL family, an example of success of other national challenging ventures, sir. And this, it was deliberated in highest level overarching committee forums that whatever learnings were there, they can be the path breaking points for the refinement in other mission mode projects, sir. And as it could happen, the most important takeaway from the simplification in the purchase procedures, which sort of, because all the consortium partners were to use their own respective procedures, that being a government entity become a sort of a handicap in the faster procurement of material and then the execution of the project. To sum it up, sir, AUSC provides better utilization of coal reserves and reduction in emission efficiency of 46% is made sure, sir. Very, very challenging. We are extremely thankful to the Government of India, Ministry of Heavy Industry, DHI, who are so kind with giving the funds to all the consortium partners, and by the help of, by their support, it was possible, sir. And it was done a mission mode, real mission mode, sir. I would like to point out to this August gathering that the total time extension what we took was only of 1 year, sir. September 2019, that is from May 2017 to September 2019 was the stipulated time period. 2.5 years, we could buy so much of exotic machines, one of its kind, material, do the fabrication, do the testing, and do the design, get the designs done, review by the competent authority, and finalize the documents. So the reviews by the high-level committees, they were very effective and supportive of the execution of the project in time, sir. Now, this gave a confidence that the consortium is ready with the design and manufacturing of the critical products of this AUSC technology, and we look forward for the coming up of the first technology demonstration plant in which we can showcase all the very hard learned, earned, established technology, sir. With this, I would like to complete this brief presentation on AU technology roadmap. Once again, I'm extremely grateful for the organizer to give me this opportunity to briefly talk about what was done under the AUSC R&D phase, sir. Thank you so much, sir.
Thank you, Ravishankar. Thank you very much. Let us see if there are some questions. I think Manchanda ji has Dr. Manchanda ji?
Yeah, I will ask something.
Yeah, please.
Can I go ahead? Ravishankar ji, very nice talk. Actually, this, in fact, I have been involved a little bit in very different technology, or rather the R&D work related to the supercritical fluid extraction, or that is entirely different area.
Yes.
But the name sounds similar, So what I am referring to is the carbon dioxide is used as the fluid, at high temperature and pressure for some variety of purposes. But now coming back to your area, you see, there we use carbon dioxide actually, but here actually we want to cut down the carbon dioxide and other greenhouse gases.
Yes.
So I will like you to just comment on that. I mean, what is your mission was to clean the fuel and then cut down the emissions actually. So that part somehow that I have missed in your talk actually. You understand my question? How much was originally the emission was there, and how much it has been reduced actually?
Sir, actually we are not in this AUSC technology, we are not cleaning the fuel, sir. Actually the same type of fuel we are using, because the fuel consumption is where we are contemplated around 20%, around 15% of the carbon emission is reduced by using this technology, sir. We are not cleaning the coal in this because that is not part of the this technology, sir. We are just because of the higher efficiencies that emissions are lower, sir. For the per megawatt or that similar type of plant what you would have built in the my colleague Virender is here. Virender, can you further comment on that?
I think per megawatt, the coal consumption is reduced significantly.
Yes.
Yes, sir.
Yeah, Virender. Yeah, please.
Am I audible, sir?
Yeah, please go ahead. Virendra, please go ahead. Mr. Virendra, are you there?
Sir, actually for AUSC plant, the plant efficiency is around 46%.
It is overall efficiency.
And the specific coal consumption is around 461 kg per megawatt hour. When compared with the 500 megawatt, coal consumption is around 542 kg per megawatt hour.
So how much is the reduction?
The reduction, you want in percentage, sir?
No, in whatever way you want to say, is it reduced significantly per
Coal
megawatt?
consumption is reduced by 15% approximately. And the CO2 emission is reduced by 17%.
Okay.
It is 15 and 17%. If you calculate the savings in tons of coal,
So far,
it is around 5 lakh tons of coal per year for a 800 megawatt plant.
Okay.
It's like a very huge quantity, 5 lakh tons per year.
So, so now, of course, I get a better picture by your this explanation. So now, what is the roadmap further? Are we going to, I mean, implement it more vigorously in the years to come? I mean, whether the mission is successful to that extent, you know, you have already demonstrated that 15% reduction in the coal consumed. So are the authorities satisfied and they want you to, I mean, push it further in the years to come? Any idea?
Sir, actually, to answer to your very pertinent point, sir, as per the cabinet note, the technology demonstration plant is envisaged as the part 2 of the project, sir. And accordingly, of course, it has to be taken up by NTPC, the utility owner, with Ministry of Power. So already initial activities had been done, and they have also made a detailed technical specification. And we had very senior level committees formed to review the specification, technical requirement, and cost optimization. What can be further avenues of cost reduction in the plant envisaged. Now, actually, in between, there is a thaw in the process that rethinking was going on, that whether AUC technology to be taken up even as a demonstration plan with the backdrop of these renewables coming up and advent of nuclear. So we are awaiting the final decision by the government to go ahead. We very much want to do, having done, as you said, sir, it is not 2.5 years. It dates back to 2010 when the PSA sponsored 10 projects were started. Almost 11 years of very hard work by the consortium partners was completed successfully. So we are very much eager to see the day when the TDP technology demonstration plant will be sanctioned, sir. We are awaiting, sir.
So my last question, you know, our Prime Minister has declared 2070 as the year, you know, where that net carbon zero that will be achieved. Do you think by that time still we will be having this coal in whatever form, whether in the AUSC form, as one of our major resource?
Sir, today we are going by the renewables, sir. So whatever renewables are there in the due cycle time, what will be the problems posed by renewables with respect to the maintenance, disposal of the material, that will come into focus after some time, sir. So certainly, not only that, we are manufacturer of thermal plants, sir, and we have done this exercise. Thermal plant are going to be the one of the critical components of our energy structure, sir. In that case, certainly, once we do the technology demonstration plant, I'm very sure there will be many avenues of optimizing it will come up, sir. And it can be much further optimized. And to give a fill up to your this thing, very pointed query, sir. Even in the phase 2 discussion, we had a lot of options discussed, that how further we can optimize the AUSC design. So once we do TDP, like it has happened in, I have been associated with the boiler side design along with my colleague, Mr. Virender, a very good performance engineer from Trichy. We have seen how we were able to optimize the even supercritical designs once we started executing it, sir. Manufacturing feedbacks, erection commissioning, operational feedbacks. So I'm very sure that AUSC will certainly find a space in the years to come, fulfilling our Honorable Prime Minister's that declaration of 2070. This one, sir. So that certainly I am very hopeful, sir.
Thank you, Ravishankar ji, and all the very best.
Thank you.
No,
Sir.
but you are Ravishankar, you are also thinking about the CCS, no, carbon capture and storage, because
Yes,
without that, I think emission cannot be controlled.
No, sir. Actually, in AUSC we are reducing the emission itself. Now, further to have a further usage of the emission, what is going, that carbon capture and the usage.
Yeah, storage. Yeah.
Yes, sir. Sir, actually, this carbon capture and storage, sorry, that utilization is a very new topic as far as country is concerned. As a R&D organization, we are also into it. We are also studying the prospects of it, and we are also planning to have pilot plant. Today in India, these are at a pilot level, sir. NTPC has established in thermal power plant of their Vindhyachal 500 megawatt. They are established a facility where they are taking in a pilot way carbon dioxide and generating green hydrogen by using electrolyzer. They are making methanol. So that is the end product. So similarly, we are also trying. It is in a very problem is, sir, carbon capture equipment almost in a power plant, full power plant level, it will add to cost like anything, like what has been.
Very true. Very true.
So we have to take it in a what we really, how much we want.
Correct.
So based on that, we have to. But in India, it's in a R&D stage, and we are participating, sir. To update to our council, sir, we are participating in the ventures.
Thank you. Thank you. Mr. Sanjay Malhotra, please. You have a question.
Yeah. Good evening, Ramano sir, and many thanks for arranging such a nice talk. Ravishankar ji, many congratulations. This consortium style of building will definitely help our nation, because organizations combining themselves, putting their best foot forward and making the things is very useful, sir. And the future lies in that only. They pool the resources, best resources. My query was, sir, this corrosion based studies loop you have put at Dadri.
Yes,
does it take care of flow velocities on the surface of the material, also the erosion part of it along with corrosion? Because these are the test benches you are building. These are national assets now. Everybody can actually go and test their coupons or their materials. So does it take care of the erosion part, because that will be key thing in this high temperature regime? Thank you.
Yeah, because, sir, that once the plan is actually in that case, as you very correctly pointed out, sir, to cut a coil after 5 years. And that's what we have done. We have, after 10,000 odd hours of operation, we have cut the coil. Samples have been cut. So certainly the erosion part also will be studied by the consortium partner along with the other metallurgical changes, what has happened due to the operation. It is envisaged, sir. And coming to one point, I just like to point out, sir, this in this case, actually, there's it is a pressure part which is put it in the system. So coupon means what you say, a small piece of tubes can be put in the system while the boilers under shutdown. So that way it can be thought of. As you said, it's a national entity. Certainly, it will be a national entity. The people can go and study that. So that's why it is there, sir. Certainly, that part is taken care of. It will be done.
Thank you.
Thank you so much.
Mr. Mehta, you have a question, sir. You can unmute yourself, sir. Unmute yourself. Yeah.
Well, first of all, let me apologize to Mr. Ravishankar for being not in a position to join in the beginning because of my problem with this computer. I must congratulate him for a very involved, detailed lecture on the material development and the testing and everything like that. And there's a variety of materials. The quality of the thing is going to be very great. And I'm sure there may be a lot of spin-off benefit to the other industries that come there. Now, I'd like to know the prototype that you have got. What is the life that you are talking about of that kind of thing? And what is the capacity of that?
The power plant life, basically, it is designed for the 1 lakh hour, that almost 25 years. So like the designs are based on the 25 years of life, sir. So, and that is boiler, the power plant will be designed for 25 years of life. The concept remains same what is in case of other utilities also, sir.
Capacity is 800 megawatt.
Capacity is 800 megawatt. The TDP plant we can have for different capacities also, sir. Capacity is not a restriction.
With this life cycle, you think the economic is quite economical?
Which pardon, sir?
With this life cycle of 25 years, you think is it going to be economical?
Life cycles are actually only thing, yes, because of the investment made vis-a-vis the advantages accrued, certainly 20 years we will be able to take it off. So because, sir, I would like to submit that the TDP we have got a X cost. Once you go ahead on the fleet mode, it has also been discussed to appraise you, sir, that various discussion happened that that AUSC when you can have the fleet mode projects. So there certainly economy of scale will come in the procurement and manufacturing also. So certainly that whatever capital investment we are making, we will be able to get it within that time frame, sir. 25 is stipulated, sir. All our projects, you know that they go much beyond 40 years. Whatever projects like our conventional project of 2 ton 500, they have gone much beyond 35 years running successfully. It depends on the upkeep of the plant also, sir.
Thank you.
Sharat Kumar, sir, you have a question.
Continuing with Mr. Mehta's question, if you have life, let's say 25 years, take it, what are the replaceable parts? Does the entire plant has to be replaced or only some parts have to be replaced?
Parts only, sir. Parts only. Parts only.
So if you replace only the parts, then will it help in some reduction of the cost? Supposing you have to replace some boiler tubes only, a few tubes or I don't know whatever, or the turbine, some parts of some blades, supposing you have to replace, will it not reduce your cost, recurring cost?
No, so actually, sir, this replacement is based on the like whatever happens, it is a part of the maintenance unless until some unforeseen problem happens. Otherwise, in our regular boilers also, we do replace the component which is especially the product which are more prone for erosion. It is replaced within every two years overall utility stake. That time they inspect for the various degradation like erosion, thinning, and other issues. They replace it. It's a part of the regular maintenance. Here, one point what I would like to submit is in the high temperature zone, we are having nickel-based alloys. There, the replacement also maybe minimum, like in stainless steel, we don't have any replacement in our boiler pressure point we have seen, sir. So similarly, the replacement also in year-to-year basis, in between two maintenances, many replacement will not be there, sir. So that way.
No, I was talking about the end of life replacement. See, I know that in maintenance, you may be replacing shaft seals and the couplings and so many other things, valve stem, seals, so many things. I'm talking about the end of life. You were saying 25 years or 40 years you will take. At the end of life, you are going to say that the plant is no good. Before you say it is no good, will you be able to replace some of the parts and get on with this? Say 40 years can be made to 60 years, for example.
It will be, sir, it has to be 40 years, too long a time. It has to be done, sir. What you say, theoretically, we have to see that scrapping the plant and by replacing, what will be the economics working out at that time, sir.
Okay.
Okay.
Thank you.
That way only we have to see, sir.
Thank you.
Mishra ji, you want to ask him the question or I will want to read it?
Just he mentioned in the end of the talk that the implementation of this project is also waiting for some nuclear. I just want to mention that high temperature reactors under development have got similar performance as far as the efficiency and the temperature. And they're being looked for the electricity production and hydrogen production. So is there anything going on in the mind? Any comparison is being made or thought of with the high temperature nuclear reactor where coal not to be used, no carbon dioxide?
Sir, at present, to the best of my understanding of this, that type of comparison with AUSC is not being made, sir. But a very valid point. I will take this point, what you have just mentioned. We will discuss with our nuclear group.
Yeah.
There's a nuclear engineering group based on Tirchi and marketing. I will certainly put up this point to them that
Yeah.
let us have a comparison of the technology,
Yeah.
where we stand vis-a-vis nuclear and thermals. Certainly that point I will take it up and get to know from them whether any activities can be done and whether it's planned. I will take that.
Yeah, yeah.
I think you should sound it to the mission director, who
Yes,
is more
sir.
competent.
Sure, sir. He has seen both sides of the coin, sir. Certainly, sir.
Yeah. So there is one comment by Mr. N.K. Agarwal. He says it's a very nice talk. Thanks to Shri Ravishankar. I wish this talk is available for our members through the email. Surely this the recorded version of this talk will be put up on our website. It will be available to you to refer to it anytime in the form of YouTube. If Agarwal, you can certainly refer to that. So if there are no more questions, I will again thank our guest today, Shri Ravishankar from Hyderabad R&D. He was very kind enough to readily agree to my request, and he took very little time to confirm and send all his details. I am very glad with the interaction I had with him. Thank you, sir. Thank you very much. We had a nice time, and the presentations were full of high knowledgeable technologies. So I wish you best my regards, best wishes to you in your future endeavor. So I give the last part of our today's evening program a vote of thanks. So I would like to thank the speaker first of all on behalf of INS and on behalf of Executive Committee of INS and on behalf of our President, S.K. Mehta, who has been a constant source of encouragement and he has been behind such technical programs in our INS activities. I would like to thank Mr. Mittal and Simjit who have been taking all pains in circulating this notification to all the members beyond INS. And in the end, I would like to bring to the notice of the viewers that the next webinar is on 15th of October. It will be given by Shri Arun Kumar of BHEL Trichy, and the topic is challenges in design of nuclear power plant components. So this will be on 15th of October. I request all the viewers to join us again on 15th of October. So thank you one and all. So I'll take your permission to stop this recording.
Thank you so much, sir.